the icebreaker this morning, we wanted to hear from you guys. What type of environmental or habitat conditions could drones help you monitor? And thank you all for your responses. With your help, we've created this wonderful word cloud that I'm excited to share with the team. And you are welcome to still participate. You can go to slido.com and type in that 5-digit code and share your response. Or if you have a smartphone, you can use your camera to hover over that QR code. So thank you all. It looks like some great responses. It looks like marshes were mentioned by a couple of folks. Same with oyster reefs and shoreline mapping. So it looks like you guys think that drones, or maybe you do already use drones in a lot of your monitoring efforts with your coastal or upland environment and those different habitats. All right. Well, let's go ahead and review today's agenda. We have 2 wonderful lightning presentations this morning with time after both of the presentations for questions and answers. Following those lightning presentations, we'll have a quick break, and then we will come back and send everyone off into breakout rooms to discuss challenges and opportunities in using drones to assess environmental quality and habitat conditions. Then we'll move right on into an exciting technology show and tell, and we'll wrap up today's session by noon. So let's go ahead and get started and transition into our lightning talks. We'll go through both presentations from our presenters today, and then there will be time afterwards for questions and answers. As questions come to you, please go ahead and type them into the chat box. I know I tend to forget the questions by the time it's time for questions and answers. So if you type them in there, it'll help us make sure that we answer those questions for you and help you to be able to focus on the presentations. Our first lightning talk today is nearshore quadcopter research, surface ocean currents, and high-frequency radar calibration, and it'll be from Douglas Call. Douglas is a PhD student in the School of Earth, Ocean, and Environment at the University of South Carolina. His research focuses on remote surface current measurements using high-frequency radar systems and occasional.
Thank you so much. So let's jump right in since it's only 5 minutes. This is a picture of one of the first drones we had. It's a little 3DR open source drone, and you can see this little antenna attached to it on the bottom. That was just for calibrating the radar. We'd fly around the radar and calibrate it that way. So today I think we're only going to have time to really focus on surface ocean currents with the drone. And so the way we estimate surface ocean currents is we're actually measuring how fast waves go, the phase speed of waves. So in the blue here is the classic, what you've probably seen in class, the dispersion relationship. And if you know the wavelength and water depth, you know what the phase speed in still water is. And there's an extra little bit from the surface current, right? So if you measure the phase speed and you know what it should be in still water, that difference is the surface current. And that's how you're going to estimate the surface current. And so choose your drone wisely. The first drones we had on the right here were not really that stable, low battery life, and they often came with these wide-angle lenses that create a lot of distortion. So we've moved on to these DJI drones. They're about $2,000 brand new for the latest model. They have a half-hour flight time and a really stable camera, and we really like to prefer them. All right, so when we were flying offshore, we took the RV Coastal Explorer from Coastal Carolina University. So first thing, check with the captain, make sure he's fine with this. And then the second thing, when using these drones, you really need to turn off all these new safety features they have. All the ultrasonic and IR stabilization, it's not going to work over the water. You can see here that we're hand launching it and we're catching it, right? So when we're coming into land, we need to catch it. Sometimes it can take quite a while. So we really recommend about 50% battery life if it's windy. Sometimes it took us as long as 5 minutes to land it, and that extra battery life really reduce the stress level when coming into land. All right, so this is the area you can capture at the max altitude that you're allowed to fly at. So with the camera we had, we were able to capture an area about 95 meters by 170 meters. And so that's the area that we can calculate ocean currents over. We use Copter Currents. It's this open source software that's been shown to be quite accurate. So you can find it on Google or GitHub and run it yourself. So the methodology is you take each frame, slice it into squares. So here we have 18 meter squares we're slicing it into, and we're capturing wavelengths here from about 10 centimeters to 10 meters. That gives us a large range of wavelengths. This is a quick processing methodology. I'm not really going to go over it too much, but basically you take that video, you're going to run FFT analysis on it, and it's going to show the dispersion relationship of your waves. And so here on the right, you can see this dashed line. That is what the dispersion relationship would be with no ocean current. And by fitting the ocean current to it, you fit that dispersion relationship to your data, and you can estimate the ocean current that way. All right, so these are our results. You can see that you're going to get some unrealistic ocean currents with the ship there, so you want to remove that. And then you're going to use the GPS and compass on board your drone to transform into UTM coordinates. And so here we have UTM transform, and these are the ocean currents we calculated in this region using about 30 seconds of video. That's about the minimum you need. And you can see this really small eddy in this energetic region near shore, which you might not expect in the ocean. You might expect all the currents to be going the same way. At other stations we flew at further offshore, you can see that all the ocean currents are going the same way on the small scale, which is probably more of what you'd expect. All right, so that day, in about 8 hours, we flew at 13 different stations, and so it was almost continuous. We'd fly, we'd go to the next station, fly again, and we were recharging in between. So 2 batteries allowed us to complete all 13 flights without interruption, and so that's what we recommend. And that's it. Thank you.
All right. Thank you so much, Douglas. And as a reminder, if you have any questions for Douglas, you are welcome to type those into the chat box, and we will answer any of those questions following our second presentation. So our second lightning talk today is tracking coastal change with quadcopters to support beneficial use of dredge material from Dr. Clark Alexander. Clark is the director of the University of Georgia Skidaway Institute of Oceanography and a professor in the Department of Marine Sciences at the University of Georgia. He is a process sedimentologist who most recently has been focusing on the use of drones to track and quantify coastal geomorphic change in man-made systems. So Clark, I'm going to pass the arrow controls over to you if you want to unmute and start your camera.
Clark,
Hey,
I believe
Clark.
you're still muted.
We are still not hearing you.
Clark, you may want to try disconnecting your microphone and reconnecting it.
How's that? Can you hear me now?
Yes, sir.
Okay, great. It's funny how when you work on it before the whole session starts, it never works out. So the motivation to the work that I'm going to talk about today is that we have a dynamic coastal system that will heal itself naturally, will provide protection for upland infrastructure, for cultural resources, but there are times where that protection needs to be augmented by the beneficial use of either offshore material for beach renourishment and dune building, or protective berm building. These are both two projects I'm going to briefly describe today. In the interest of time, I'm going to just cover them and to give you a sense for the kinds of work that we're doing with drones in the coastal zone. This is work that I'm doing with Claudia Venherm here at Skidaway and Colby Peffer, who was at Skidaway and is now down at Georgia DNR. And these are projects that we're working on collaboratively with the Corps of Engineers, National Park Service, Georgia DNR, and the city of Tybee Island. So Dave Johnson on Wednesday covered these kinds of questions about why you would want to do drone monitoring and what the advantages are. He did it very well, mentioning affordability. My first point here is his point of immediacy. The quality is my accuracy statement, but I'd like to add that there's also the repeatability that aerial monitoring methods that are easy to implement bring to monitoring of these kinds of very dynamic systems. So you can look at how did a beach change or a dune system change before and after a single event, which really wasn't possible with larger scale platforms. And then the last two bullet points really lead to one last word, which would be applicability. That, yes, there are assessments that can be done with these kinds of tools, but there are also very applied kinds of questions that can be answered to look at the long-term behavior of built systems. So our workflow in terms of working in all these systems that I'm going to talk about today is we use Pix4D to capture and mission plan. We collect about 2,000 images in our each of our study sites, which are typically around a tenth of a square kilometer. At the same time, we collect ground control points with RTK GPS, and then we bring that all back into the lab, stick it all into Pix4D Mapper, which is our tool of choice, although there are a number of different ones out there. Then Pix4D will put out a point cloud that we can bring into ArcMap and use that to develop a digital surface model. It's very important to differentiate between a digital elevation model, because if there is vegetation or buildings, you're only going to be seeing the surface, not the land surface. You're going to see all the surfaces that are there. Within ArcMap, we can do our surface area evaluations using our RTK accuracy points that we've collected at the same time. Then we can use ArcMap to both develop elevation profiles and develop patterns of elevation change using raster math tools, with which we can look at volume change. And so these are the things that are the applicability that I'm mentioning, is that being able to take our digital surface models, take them through, okay. So that's the workflow. These are the parameters that we use. In general, the important things I want to point out, we're using DJI Phantom drones as well. We're looking at the RTK model now, and we'll just talk about these details if people are interested later. We're going to look at Tybee Island and Cockspur Island, where beneficial use dredge is being used. Tybee Island just got renourished. While they were being renourished, they pumped extra sand up onto the beach, which is being put into artificial dunes to protect the island. We've just started this project, so we only have 2 time points right now, but you can obviously see the difference between the created dunes and the naturally occurring dunes on the island, and you can see things like overwalks that have been created since the dunes were created. Also, just to speak briefly to the point of the level of accuracy you can achieve, here's a bunch of car tracks on the beach with one of our control points, and you can see that you can actually see those car tracks all within a 25 centimeter range, so you can identify very fine scale changes in these features. Cockspur Island is a second example. It's an area where there were historic features. Oh, come on. Can't move the little arrow. Oh, well. So there were historic features just south of the sand berm you see in the upper right panel. If in the lower two panels, you can see there's something called the North Pier, which was being eroded over time, and the Corps of Engineers pumped that dredge spoil pile up there. The top panel on this figure shows the area before the sediment was deposited. You can see it's very deep throughout with those blue colors, with the North Pier being located right here. Over and after deposition, the second panel on this figure, you can see a large sand berm where there was up to 4 meters of sediment deposited. Now I'm going to show you 3 panels in quick succession, and I want you to track that long linear feature as it retreats to the east with time. And so what you see there is the loss of this sand berm over time, and if we do cross sections through that sand berm, you can see the red color shows the before level of the bottom. The blue up at the top of the panel shows post deposition, and then you can see through the sequential colors the erosion and removal of that material over time, and the retreat rate of the berm itself in line 4 down here. Using that retreat rate, we calculate that the berm will be present and effective for something on the order of 14 years. Looking at volumetric changes, we calculate that berm will be present for about 18 years. But what we're really seeing is that the berm in most places is deflating and becoming less effective at providing protection. Even though a lot of the sediment is still remaining, it's just filling in this area that was very deep and providing some level of protection, but not the level that we would like. So I'm just going to leave it there with these same questions and answers for why UASs are useful for monitoring man-made deposits of sand. One other thing I will point out is that we were doing our work monthly, but we found that the changes during much of the year were too small to observe on monthly timescales. So we find that doing it on quarterly timescales is much more useful. And at that, I will leave it be.
Thank you so much, Clark. We are going to go ahead and open up some time for questions and answers for both Douglas and Clark. And I have a question. Douglas, we'll start with you. Have you been able to compare the results with the near buoy data?
So, no, we haven't compared it with the buoy or the radar, actually. I thought that was another question. We just weren't in the radar coverage area, but we had an AECT on the boat, and they compared well when we were not in the plume. When we were in a plume, it was a really thin top layer that was actually going at a different velocity, we think, than where the AET picked up about 1 meter to 2 meters below the surface. So we're measuring very near surface currents at about 20 centimeters depth with the drone.
Thank you. Great question. And that does also answer Deborah's, I believe. And Clark, we've got a question from Gary for you. Are your oblique angle shots redundant? For example, combined nadir and oblique for same area?
Yes, they are. We do about half of our observations, our photos, are oblique and half are nadir, and we have about 80% overlap, so we have multiple frames that cover the same area.
Perfect. And what elevation are your flights performed at, Clark?
We're flying at 50 meters, I believe, 75 meters, something like that.
Okay. I see no other questions right now in the chat box. So please do just take a moment. We have some more time for questions and answers if you have any questions for either Douglas or Clark to share those in there. A lot of excitement of the application that you guys are using.
Clark, can I ask you a question?
Yeah.
So I saw you had the Phantom 4 RTK. Are you able to do that without any ground control points, or would you lose a lot of accuracy?
We're still comparing it with the points. It's a new instrument to us. We had some trouble getting it to connect to the VRS network for a little while. We've worked out those issues now. Had a lot more to do with the mount points at the VRS service as opposed to the RTK drone itself. So we've only used it a couple of times, so we're trying to build up a large enough data set to do that comparison. I'll let you know.
Yeah, that'd be interesting. Thanks.
Good question. Clark, do you have any questions for Douglas?
No, I just think what he's doing is cool. That I've always thought wave radars were cool, but now to be able to do it with a drone out in the middle of the ocean, that's awesome.
Yeah.
A little more nerve-wracking than sitting at home looking at my radar data, though.
Mm-hmm.
Clark, we do have a question that just came in for you in the chat box. Are you seeing changes in beach management with the results from this project?
Well, the Tybee Island project is just getting off the ground, so we haven't really had time to provide input to the managers. That's part of the goal, is to see where the newly created dunes are changing, how fast they're changing, and what areas of the Tybee Dune system do they need to be thinking about recreating sooner rather than later. The project at Fort Pulaski, we have provided the results to the local DNR and to the Park Service and to the Corps. They're using that information to try to plan how often do they need to renourish that berm, and I think the answer is pretty soon.
That's really great that this strategy will hopefully be able to help with some management efforts.
Mm-hmm.
Thank you.
Well, I find that very appealing myself, that because we can go out and do this so quickly in a relative research sense, that we can provide pretty rapid input that can be used for doing better management.
Absolutely. And it looks like several people in the chat box agree with you.
Thank goodness.
Makes you feel good about going out there every day. We've got a few more comments that look like they're coming in. A question for Douglas. Would super high frame rate be beneficial? Some UAS cameras can push it to 500 plus FPS.
No, we're actually looking for resolution. We actually take our 30, we're shooting at 4K 30 frames a second, and we're actually taking that down to only 10 frames a second just to save on data. And so the waves are not going that fast, right? They're only going about 5 meters per second. And so you really only need 5 frames per second, max. Yeah. Interesting question, though.
All right. Well, thank you, and thank you for wonderful questions, everybody, and thank you to both of our presenters. If you do have any questions for them that you think of throughout today, feel free to type them into the chat box. We are going to be capturing the chat box and can always send those questions. So let's go ahead and transition into our Unoccupied Aircraft Systems Technology Show and Tell with Dr. Dave Johnston and Justin Ridge from Duke University's Marine Robotics and Remote Sensing Lab. Dr. Johnston is an associate professor of the practice of marine conservation and ecology at Duke University, and All right, let's go back to the slide. At Duke University, and he is the director of the Duke Marine Robotics and Remote Sensing Lab. Dr. Johnston's research focuses on the ecology and habitat needs of marine vertebrates in relation to pressing conservation issues such as climate change, habitat loss, ocean noise, incidental mortality, and overharvesting. And with him today in our show and tell will be Justin Dredge. Justin is a research scientist leading the coastal mapping efforts for the Duke University's Marine Robotics and Remote Sensing Lab. His work focuses on using remote sensing technology to monitor oyster reefs and wetlands in relation to sea level rise and other environmental factors. And with that, I will go ahead and turn everything over to Dr. Johnston and Justin, and they're going to share and tell with us.
All right, thanks, Caitlin. All right, we are gonna kind of like split this up a little bit and go through some of the products that we've been working on in some of our projects and just give you sort of a virtual tour of how you process some of these data and what it looks like. And Dave, I don't know if there's anything else you want to share before we dive in. No? Okay. You guys can hear me okay, right?
Justin, we can hear you. Dave, if you're speaking, we can't hear you. You may want to try disconnecting your microphone and reconnecting it.
How about now?
Now, there you are.
Okay, sweet.
So Dave, was there something you were going to say?
No, I was just going to say no. Thanks for the introduction. It's great. I'm looking forward to being able to show people some of the data that we've been talking about and was presented earlier. So it's nice to be able to get that visualization part.
All right. We haven't started sharing anything, so we are going to jump in. We're going to just go through like a couple examples, and this is going to get at some of the stuff like that Clark was talking about earlier with the software. And so let's go. All right. Everyone can see my screen?
Yes.
All right, so the first example we're going to get into is here in North Carolina. We're in the Cape Lookout region. I'm going to zoom in here a little bit. So this island is Pivers Island. This is where Duke Marine Lab and the NOAA Beaufort Lab are situated. And then this stretch of sand is part of the Rachel Carson Reserve, part of the North Carolina National Estuarine Research Reserve. And this bird shoal is one of our study areas that we've been monitoring over the past couple years, just kind of understanding how it's changing with long-term processes and storms. And so I'm going to show you one of our missions that we conducted over this. This was a mission that we flew over the area just before Dorian came. So we were kind of collecting a pre and post storm missions for just doing an impact assessment, which Dorian thankfully did not do too much to our area, unlike Florence. But this, what you're seeing here is Pix40. And Pix40, this is all the red dots you see are essentially the pictures that were taken in our mission. And this actually is 3 flights that were done with an EB-RTK. And I'm just going to pop right into. So basically, what happens is during structure for motion, the software is taking all of these overlapping images and it's identifying unique pixel clusters in those images and then tying them together across those images to create both a stitched orthomosaic and actually a 3D model based on triangulating each of those points across the images. What you're looking at right now is this is the point cloud view in Pix4D, where you're seeing all these green and red dots are associated with each of the images that were taken during the mission. And if you click on one of these images, you can see over here on the right side, this is one of the stills that was taken, where you have like a vegetated dune environment in the beach. And what it's showing you here are those key points that were generated on the images, basically as it identified unique pixel clusters across those images. And you can just see just how many thousands of key points were identified across those images. And just the number of key points that were identified helps in that whole process. When you see the red cameras, that's essentially those were images that were taken over water. And we can't really piece together, there's no unique pixel clusters that can tie together across a lot of these just open water pictures. So they are left out of the final product. All right. So when you, this is basically the tie point cloud. So it's the key points that were generated to create the skeleton of this island area. I'm just going to rotate this. And so after it's done creating the tie point skeleton, the next step in the process is to densify the point cloud. Basically go through all the images and generate the rest of the points that will fill out the point cloud. So this is the densified point cloud. And all the pixels are colored based on the images. And so now you can see how this reconstructs the whole island environment. This island is approximately 4 kilometers in length. And we have on the west end a vegetated dune environment that's mostly just it's a dredge spoil area. And then here in the central region, this is the most dynamic area where we're seeing a lot of overwash occurring. And this is very low-lying dunes that have been stripped several times during different storms. And then as you kind of march along farther east, that's actually where the island has been expanding. It's been, all that sand is starting to kind of grow the island eastward. All right. So it's pretty interesting to come in here and navigate around the point cloud, and you can kind of see how well it's recreating these three-dimensional surfaces. This, you can see, is the dune scarp that's forming, where this is an erosional area. And so there's been a lot of change along this dune shoreline. And then you can see over here in the lower lying dunes, not much relief. And just to give you an idea of kind of the level of detail you're picking up here, these are oyster clusters that are back behind this area. And we're actually, this overwash is starting to bury some of these oyster clusters. We've lost a couple reefs behind the island here that have been buried through the overwash events. The green little dots you see that are kind of popping up all along here, those are actually our ground control points. That's something that you saw in one of Clark's images. I'll just populate one of these. They are what help us tie everything together. We actually flew this with, because as I mentioned, we flew this with the EBRTK. The initial model is actually pretty good before you even use the ground control points to help further increase the accuracy of everything. And so that's another reason why this is actually a pretty low number of ground control points you would probably use over this size of an area, but having a survey-grade GPS on the drone helps to reduce the need for that many ground control points over an area. Something that Pix4D does, and I should mention that a lot of these things are also true for other processing softwares like Agisoft, but you can see this, and Pix4D's counterpart in Esri is Drone2Map. So that's essentially the same software packaged in for Esri. Pix4D does do point cloud classification, and I can just kind of show you like what that looks like, where you can see the vegetation. It does very well picking out shrubs and trees. It does not do well picking out like smaller, denser vegetation like grasses, like you would find in a marsh. It's not very useful for that. It also identifies sand as road surface a lot of the times. But when it does this, this is one of the ways that it generates a digital surface model, and then it can also generate a digital terrain model, DTM, using this point cloud classification. And I can show you, I'm just going to pop in here and show you. So here's the ortho that's generated from the stitched imagery. Zoom in here and see how fast it loads like some of these details. So you can see you can pick up quite a bit of detail from this. And these flights were flown near the ceiling, so near 120 meters. There's the oysters. So there is the mosaic that's generated, and you can also view the DSM, the surface model, which here you can see the differences in the higher vegetated dune areas and the lower low-lying dunes. And then this is the surface model, so it's still including the vegetation in that model. I'm going to switch over to, trying to keep an eye on time here. Another area that we've done, we were conducting some flights down in Belize over some mangrove habitats. So this is a mangrove island in the Port Honduras Marine Reserve that we flew both an RGB and a multispectral flight over. And so this is the RGB point cloud that was generated. And so here you can see how well you can kind of pick up the different, this is mostly a mangrove covered island, but there are areas in here where you have coconut palms. That's one of the things that they're interested in, just kind of keeping track of. And this is the boat. When you have moving objects in your images, so the boat was kind of shifting around in the water, it does some weird sort of ghosting effects with that. When you look at the classification that's done with this, it does a pretty good job of classifying these. It does the mangroves, it works pretty well with, at least for this. And it identified some sort of building with those towers that were on the island. When you look at the products here, so here's the mosaic that was generated. You can get down in here and get some pretty good details of the different vegetation. This is flown at about 80 meters with a DJI Phantom 4, just for give you some context. And then this is the DSM that was generated. Again, the vegetation is all included, but then when you look at the DTM, because we classified the point cloud and had it generate a DTM, it had this nice smooth surface of that island. And just to show you sort of, so again, I said we flew this with a multispectral camera. We were using a actually for those of you that were present on Wednesday, Julian showed one of our Phantom 4s with a Sequoia multispectral sensor attached to it. So that's what this flight was conducted using, that drone. This can give you an idea of the multispectral data that was generated from these flights. This is looking at green reflectance. And so white is more reflectance. Red, it collected red edge, and near infrared, which near infrared is really good for sort of like parsing out water from other things. And then near infrared and red are what factor into the normalized difference vegetation index, which a lot of people use to sort of give an indication of vegetation health. And that's a ratio of near infrared and red reflectances. And so that's automatically generated in Pix4D when you process these data. So this is the NDVI for that area. And Pix4D is pretty nice if you have other indices that you want to calculate. You don't necessarily need to do that in ARC. You can actually have Pix4D go ahead and calculate it by creating a new index using some math between the reflectances. How am I doing on time?
There are about 15 minutes for anything that you and Dave wanted to share.
Okay, because Dave's going to share some too. I'm just going to really quickly just breeze through this. One of the examples of habitat mapping that we've been doing using the drone data has been using new deep learning methods for analyzing those orthomosaics. And for those of you that deep learning is a type of artificial intelligence that computer vision where you're basically training the computer to learn sort of features. And it does this through an iterative process where it kind of continually learns kind of more intricate features. And there's all these layers that happen with deep learning. And we did this within the Rachel Carson Reserve that I was talking about earlier, flown with the ThinSply Eevee. And through this process, we manually labeled all of the oyster reefs that were in the area. So a student went through and manually labeled all the oyster reefs that she could find. Then we broke it down. We basically split the whole area through this process. We tiled it. And so the deep learning process involves training the model. And so you'd have to split the data into these sets that you would train it on, and then you would test it on. And then you would validate it with a final independent data set. And so we would create the model with training data and validation data, and then we'd have a data subset that was testing data. And so during the model development, we would train it. We would actually augment the images. And when I say that, I basically mean we took images and we changed them. We added contrast. We made them noisier. We flipped them just so that as it's learning features, it's not heavily reliant on, we're kind of giving it a little bit more flexibility. And then we test it, and it would, we did our final test in the model output and compared that to the manual data that we had generated. And so this is just sort of a comparison between the manual input and what was generated from the model here. And that we saw very good results, and actually to some degree we found that it was picking up oysters that we had actually left off of the map. And so it did a really good job. And it predicted approximately 8% more oyster reef area than we had manually delineated. There were minor instances of false positives, but a majority of those, of what was seen extra, were oysters that were not identified during the manual process. All right, I'm going to hand it over to Dave now.
Thanks, Justin.
Stop sharing.
Hey everyone, can you see my screen now?
Yes, we can.
Great. So Justin did an amazing job, sort of walking people through the Pix4D interface. And as a complement to that, I want to show you how you can use Pix4D, but it's cloud-based tools to be able to run those things, but also share them with people. And so I have a couple of data sets that I'm going to share with you, I'll put them into the. Hopefully, there's a link box in the Google or the Adobe Connect that I can paste those into so that people can actually go and hit them. Is that the case?
Yes, there is, but while you're sharing your screen, you may not see it. So feel free to either put them in the chat or pop them in this box over here to the right.
I'll put them in the chat. I think that's probably going to be the easiest. First one there. And so this particular model that I'm going to show you is actually from Pybers Island, right near where we are, just actually off to the edge of it. And so you can see that model hopefully now. I'll zoom it out a little bit. The nice thing about the cloud is that you can share a link, right? So that people can actually go and check out those data at the same time. You can do the same types of visualizations that you saw that Justin was doing as well. And for those people that are signing in and checking out the data, there's a set of tools that you can use to be able to actually make some measurements. So if you wanted to measure the area of a particular feature fairly quickly and share that information with a colleague, then you can actually do that. And if you look over here on the right-hand side, it provides some information about that right away. It gives you the 2D and 3D area that's associated with it, the perimeter, and it'll have some elevation information. In this case, it hasn't been ground truth to an Earth model properly, so those values are a little bit wonky. But that's it's a really nice set of tools to have so that you can share things with people and get the data out into their hands quickly to be able to visualize the work that you might be doing together, to collaborate, and to brainstorm and think about what you might want to do next, or what areas that you might want to focus on over the next set of surveys that you're going to do. You can also do volumes as well, and so it's just a really nice way to be able to share those kinds of things. This is the 3D view. Just as Justin showed you, you can also load the orthomosaic, and you're able to go in and you can see these areas. I just got rid of a couple of those polygons, but zoom in and give you a sense of resolution that you can generate through these kinds of surveys. Okay, so first example, kind of in the coastal zone here. Next step for me is to take you to a different place, and I'm going to take you to a penguin colony on the Antarctic Peninsula. And for folks who may have been down there, This is a place called Nico Harbor in Anvord Bay. It's beside a very active glacier. We have been working coastally in these areas using drones to be able to essentially develop methods for sort of biogeographic assessments of these locations, with a focus on things like penguins and seals, and also sort of emerging vegetation and changes in things like snowpack. And so this is a really interesting colony. It has quite a bit of relief to it. And if I zoom in a little bit and kind of rotate around, you'll get to see that it's kind of a cool sort of rocky area. This is late in the season after most of the penguins have left. And you can see several sort of breaks in the snowpack that are indicative of paths that birds use to be able to go from the colonies down to the water. If we zoom in a little bit here, you get to see us as researchers on the beach. And for anyone who has kids that play Minecraft, this probably looks remarkably familiar. If we take a look up over here, we can have a look at the areas where the birds are. The color that you're seeing there, the pink, is guano, which is one of the great tools for us to be able to identify colony areas, because it's very easy to detect in multispectral imagery because of its color. And you can see individual birds, some of them attending nests still, some of them actually on the ice or on the snow, and in some cases kind of lying down on the snow and cooling off because it was quite a warm day. So very sort of cool tool to be able to share this with colleagues, especially if you're thinking about, population assessments of coastal seabirds, and certainly starting to understand the three-dimensional habitat relationships that are associated with the colonies themselves. Okay, so a cool example from the Antarctic Peninsula, and a really nice, I think, very great way to visualize a colony of this type. I'm going to do another seabird example now, and actually jump to the Falkland Islands, and in this case the Steeple-Jason Islands, which are on the very northwest part of the Falkland Islands. And so again, this is a 3D point cloud generated from a series of surveys. These were actually done with a combination of Phantom 4s and also Sensefly EBs. And so to give you a sense, this area that you see here, which is essentially spanning the area where these birds are, it's about 90 meters. And in this case, this is a black-browed albatross colony. And as I sort of zoom in a little bit here, you'll start to see the individual birds sort of populating in as the web interface is loading higher resolution points into the browser. And as we zoom in a little bit more, you're eventually going to start to see this incredible mosaic of individual birds on their nests. And we were given a great presentation earlier by Clark that showed the elevation of the deposition, or the ruts from tire tracks. Well, in this case, these bumps are individual albatross that are being resolved in these surveys. Okay. So again, another nice way to be able to share that information, and just by looking at this, you probably get the sense of the enormity of the task of having to actually try and enumerate, say, an albatross colony of this magnitude. And so the last thing I want to do is just quickly sort of mirror what Justin did and talk a little bit about the deep learning process that we've applied. And I'm just going to touch on this briefly because we're going to deal with it more a little bit later in the webinar. But just to give you a sense of what it looks like to be able to count a colony like that through deep learning methods. So I'm switching now to an ArcGIS map, and I'm going to zoom it out quickly, and just to give you a sense of where we're at, the Falkland Islands in relationship to South America. If we zoom in, we're starting to see the actual outlines of these colonies in those orthomosaics, and you'll see some color patterns. Hopefully that one. I'm going to reload it.
Hey, Dave, we've also got about 2 minutes left.
2 minutes, okay. I would want to zoom in really quick just to give people an idea of what that deep learning model looks like to be able to count these birds. So we zoom in closer and closer. You'll see these little yellow boxes start to tile in. And I'm going to pick a spot that's kind of close to the vegetation here, and you'll actually see some boxes that are detecting these albatross. In some cases, they're double detections because of the way the tiling works, and we get rid of this through a max suppression algorithm afterwards. But this allows us to be able to essentially count colonies of hundreds of thousands of birds in a very, very short period of time from drone imagery that's collected by, from aircraft that are quite inexpensive and easy to fly, even in locations like this where the weather can be a little bit temperamental. The other cool thing is that we can actually run models that detect multiple species, and in locations, in some places we have both penguins and albatross in nesting in similar locations, and the models are able to actually pick out between those two because they've been trained on both those species. I'm going to stop sharing right now, and I'm going to put these URLs into the chat so that people can go and take a look at these data and mess around with them themselves. And I think hopefully you'll enjoy that, and it'll give you a sense of the utility of these web interfaces for working on these data and sharing and sort of developing your collaborative process.
Great. Thank you so much, Dave and Justin. This was phenomenal. I know that reading through the chat, everyone is equally as amazed as I am. And Dave and Justin have been doing a really great job answering questions that came through the chat box. So if you did pose a question earlier in the share session, check back into the chat box to see if it has been answered. I have been keeping tabs, and it looks like they all are. So and you are welcome to keep typing in there because I see that Justin and Dave are also still typing in there. So feel free to ask any questions there. And with that, we are going to wrap up today's virtual sharing or virtual session. Thank you all for joining us today, and thank you to our presenters. There were great presentations and resources and conversations shared. The notes from the breakout groups, as a reminder, are going to be projected at the end of this meeting for anyone who's interested in viewing them. And if you'd like to add something, you are not going to be able to add in the notes. You can add any additional comments in the chat box, and that will be documented. Please take a moment to complete the session evaluation that is on your screen. That'll be up for 2 minutes before we transition over into the notes. And our next session will be on Tuesday, October 20th at 10 o'clock a.m. until noon. Eastern Time, and it will be on incorporating training into your drone program and coastal hazard and damage assessments. And just to give an overview of what to expect on October 20th, the agenda is there on your screen. And with that, I will stop talking and let you guys respond to the evaluation and share any additional comments. Thank you all, and we'll see you next time.